The extreme point theorem. What do we mean by extreme point? Actually, they are the corners. We have seen before a convex set with corners, right? The corners are called extreme points. Simply, this is what we mean. Let me make it quick and easy like that. Assume we have such a convex set. This is convex set. Then these points are the extreme points. Simply. Okay. Why? Because they are, any one of them is not on a line segment joining any other 2 points in the convex set. You see that? No one of them lies in a line segment joining a pair of points in S, okay? And any other point in this convex set, say for example, this red point here is not extreme because we can find 2 points here and here, for example. So that if we connect, we will find our original point on the line connecting them. So, sorry, I'm trying to make this a little. Okay, choose another point. If we choose this point, for example, we can find 2 points on the convex set, say this one and this one, so that if we connect them, then our point will lie on the line segment. So both of these 2 points, this one and this one, are not extreme. Not extreme points, because they are not corners. And also, any point on this line is not an extreme point because it is on the line joining 2 other points. So also this one is not extreme. Okay. So we will introduce the concept of extreme points or corners. Why we need them? Because they are candidates for solution of the linear programming problem. They are candidates for the optimal solution. So we need to look for the corners. Okay. So the graph of each constraint, remember that of an equality is a closed half space. Remember, inequality, it is less than or equal or greater than or equal. The constraint, when we take, is a line or a plane. When we take one of the sides, we call it half space. But when it is equality, we call it plane or hyperplane when we go to more dimension than 3. We have seen this before, okay? Now, the set of all points, that satisfy the whole constraint, all the constraint, is exactly the intersection of the closed half spaces. And we have seen that also, okay? But we will call this set to be, which is a convex set, we will call it the convex polyhedron. Convex polyhedron. And it is indeed a convex set, and we have seen this before. Actually, we proved it. Okay, so we will define the convex polyhedron. What is it? Is the set of visible solution for linear programming problem. The set of visible solution, okay? So we talked about the set of visible solution before, but we will give that set a new name. Convex polyhedron, okay? Good. Now let us define a convex combination. We define the convex set. Remember that convex set is a set that contains, do you remember this? So S is convex, a set S is convex, this is a set if whenever if we choose any 2 points from S belongs to S, then the linear combination must also belongs to S. See this for where lambda is any number between 0 and 1. So either this happening, or we can say for any x1 and x2 belongs to S, c1 x1 plus c2 x2 must also belongs to S for any two numbers c1 c2 positive non-negative with their addition equals to 1. Okay, so this or that, this is the definition of convex set. Okay, good. Now the following definition will tell us the following. Assume we have points, say this is x1, this is x2, x3 maybe somewhere, x4, maybe x5 here, and so on. Okay, now these are just points. Now I want to form a convex set out of these points, which means I want the smallest convex set that these points make. Okay, which means I want all the possible convex combinations of these points, x1, x2, x3, x4, and x5, all possible convex combinations. In fact, that includes any point that could be on a segment, a line segment, joining two of these, or any other joining 2 points that come out of these. Let me explain that. Actually, what I am saying simply, say this point, for sure we will take it because it is on the line segment between x1 and x5. Say this point, we will take it because it is on the line segment between x4 and x5. Say this point here, is it on the line segment of some between x1 and x2? Okay, it looks like the line segment between x1 and x2. Okay, let me choose another point like this one here. This might not be on the line segment of any two of these points, but if you pay attention now, we can make a point here which is on the line segment between x3 and x4. So it is in the convex set we are working on, and we can make another point here which is on the line segment between x2 and x5. Good. Now we can make, so this new point, the orange one, is also in the convex set we are forming. Now we can join these two new points and then get our point here. So this is in the convex set. So we keep doing that all the time, and then the remaining, the resulting actually will be simply, let me erase everything I made there. We are looking for the convex set that contains, we are looking for, or we are trying to form the smallest convex set that contains x1, x2, x3, x4, and x5. and simply it is this one. Just join them like that, like this, like this, like this, and that with lines, and then all the points inside here are in the convex combination of x1 to x5. Convex combination, which means any point here can be obtained as a linear combination of x1, x2, x3, x4, x5, and not any linear combination. The coefficients must equal 1. Okay, now this is the definition. A point x, so this is our point here, is x, okay, is a convex combination of the points x1 to xr in Rn. If for some real numbers, if we can find real numbers c1, c2 all the way to cr, because we have r points x1, x2 to xr, that satisfy the summation of these numbers equals 1, as in here. Okay, all of them are non-negative, such that we have x, the point here we are talking about as a linear combination, as a convex combination, is a linear combination of the x1, x2 till xr, and the summation of the coefficient equals 1. That's why we call it convex combination, because the summation of the coefficients in the combination equals 1. Okay, so a convex combination, we will use that. So x equals c1 x1 plus c2 x2 all the way till cn xn, with c1 plus c2, take this coefficient, must equal 1, and every one of them is a negative. Okay, so this is the convex combination theorem. The set of convex combinations of a finite set of points is convex. This is what I have explained here. I said that the set of convex combination, all of them together, of x1, x2, x3, 4, 5, will make a convex set. So I said that, but we did not prove it yet. Okay, so how to prove some set is convex? It is written to the left. Okay, thank you. Come back. Okay, so how to prove a set is convex? Now it is shown at the left. So we will choose 2 points. Let us say here in the proof, this is an exercise actually, but I will do it for quick. Let S be the set of all convex combination of x1, x2 all the way to xr. Okay, now want S to be convex, right? Want S is convex. How we show it is convex? So we choose 2 points, x1, x2, but we will give them different names because we are assuming that we are using x1, x2 to xr. So what we do, we choose 2 points, let's call it y1, y2 belongs to S. Each one of these is in S, so y1 is a convex combination. Say it is c1 x1 convex combination of these x's, correct? And y2 is a convex combination. I will say it is d1 x1 d2 x2 dn xn. Now here the summation of the ci equals 1 and the summation of the di equals 1, and each one of them is non-negative. Now remember what we want us to be convex. That means now we want what? We have chosen 2 points here, then we want lambda y1, as we have seen here, lambda y1 plus 1 minus lambda y2 to belong to S for any lambda between 0 and 1, right? Okay, but what this equals, now consider, what does it mean to belong to S? We want to show this is a convex combination of x1, x2 to xr. So let's see that, lambda y1 plus 1 minus lambda y2. Okay, so let us replace y1 and y2 but by what we have there. So it is, I will use a summation notation. So it is lambda times ci xi, summation I from 1 to r, plus 1 minus lambda summation di xi, I from 1 to r. Now play with that. What we get, we will get summation of, now we have xi in here, xi in here, okay? So we have xi multiplied by what? Let us see. Lambda ci plus 1 minus lambda di. Agree? I equals 1 to n. Okay? Now we are done if we show this thing here equals 1. Right? Because that will make this combination, this element is a combination of the xi's with coefficient summation equals 1. So I will leave this to you to show that this summation here, all the summation equals to 1. So this thing here is a convex combination of x1 all the way to xr, so it belongs to S. Good. So we started with y1 and y2 belongs to S, and we ended up with lambda y1 plus 1 minus lambda y2 belongs to S. This one here. Okay, so S is convex. So S is convex. Okay, any one of you has any question? Okay, now we go to the definition of extreme points, corners. A point U in a convex set, a point U in a convex set is an extreme point. This definition will go with us for the remaining of the course. It's an extreme point of S if it is not an interior point of any line segment in S. Okay, so it is extreme point if it is not on any line segment joining any 2 points. That is, U is an extreme point if there is no, so the line segment is of that form. If there is no points, distinct points x1 and x2 such that U equals lambda x1 plus 1 minus lambda x2, which means for some lambda which means U is not in the line segment. There's no 2 points to that U in the line segment between them. Okay, so to prove U is extreme point, we will do that. U is extreme point if and only if, let me write it in mathematics notation, there is no x1, x2 in S such that U equals lambda times x1 plus minus lambda times x2 for any lambda between 0 and 1. Lambda here does not equal 0, because if it equals 0 give us x2. If it is 1 give us x1. So U, it is either x1 or x2. We don't want that to happen. Okay, we want U to be strictly on the line segment joining x1 and x2, but not x1, U not x1 and not x2. So we did not allow lambda to equal 0 or 1. So okay, lambda is an extreme point, sorry, U is an extreme point if there is no such x1 and x2 doing that. Okay, we will use that to do proofs. And as you can see, I made a figure. This is an extreme point. These are all extreme points. Now, and this convex set came out to be an intersection of closed half spaces, right? Okay. Now, let S be a convex set in Rn. A point U is an extreme point if and only if it is not a convex combination of points of S. So let us prove that. It is an exercise for you to do, but I will sketch a proof. It asks us to show that U is extreme. Let me write the theorem here. Extreme point if and only if U is okay, let me write it this way. If and only if U does not equal C1 x1 plus Cn xn for any Ci positive with summation of Ci equals 1. Okay, so U is not a convex combination. Okay, so this direction is direct, easy by definition. If U is not a convex combination of any number of points, then U does not equal lambda x1 plus 1 minus lambda x2, which means U does not lie on any line segment of any 2 points. So U is an extreme point. So this is direct from the definition. Notice this does not equal. So U does not equal any linear combination, convex combination. So U is an extreme point. Okay, U is an extreme point. Now we want to prove the other direction, this direction here. We will do it by contrapositive. Which means we will do it the following way. We will do we will negate this part and give the proof of that part. So we will say U is a convex combination. We will prove U is a convex. We will assume U is a convex combination. That means U is not an extreme point. This is what we want to prove, right? So let us start with that. Assume, let me change the color here. Assume U is a convex combination of some points in S. Say U equals C1 x1 plus C2 x2 plus Cn xn with Ci not negative, and summation of Ci equals 1, I from 1 to n. I called it n here. Okay, now we want to show U is not extreme point. So we want to write U as lambda times some x plus some point in S plus 1 minus lambda times some other point. Okay, what we do here, one of these C's must be non-zero. We cannot assume all of them are zero, right? Because then we will not have a linear combination. One of these C's must be, at least must be non-zero. Which one? Well, we can assume it is the first one. We can reorder, change the order, and then we change nothing. So we may say assume C1 is greater than 0. Then what I want to write C1 x1 plus, now the idea here, this is my lambda. Now this is C1 x1. Now I want 1 minus lambda here, 1 minus lambda here, multiplied by some other vector. So I want 1 minus lambda here. Lambda is C1. I chose lambda to be C1. So 1 minus lambda will be 1 minus C1. But the question now, what I multiply this with so that I change nothing. So look here, I have choose C1 x1. I took that part here. Now, okay, the green part I want to transform it to here. What I do? What I multiply this with what? You can guess. Just make the one underlined with the green, rewrite it so that it is 1 minus C1 multiplied by something. I think you can guess this will be C2 over 1 minus C1 times x2 plus C3 over 1 minus C1 times x3, and then we keep going till Cn 1 minus C1 times xn. Good. So I got this. So lambda times x1 plus 1 minus lambda times another point inside S, right? This is inside S. This thing here is inside S. Why? Because it is a linear, it is a convex combination of elements x2 to xn. So U is lambda times some point in S plus 1 minus lambda times some other point in S, and therefore U is not an extreme point. So what happened? We assumed U is a convex combination, and then we said then okay, U is not a convex, not an extreme point. So good. Okay. Anyone has any question? Let's go to this theorem, which we will not prove, only we will consider and try to understand. The extreme point. Now, what we want extreme points for? Let S be the set of visible solutions to a general linear programming problem. Okay. Now, if S is non-empty, you know that S now is a convex set. Okay? Now, if S is non-empty, which means it has elements, and bounded, then the optimal solution to the problem exists, and it occurs at an extreme point. So when we have a problem in general, we will say before we start looking for a solution, we will ask, does that system, the problem, does it have a solution? Now this says if the visible set of, does it have an optimal solution? Sorry, this is the question. Does it have an optimal solution? Now it says if the set of visible solutions is non-empty and bounded, that convex set is bounded, then the system, the linear problem, has an optimal solution, which occurs at, so it has an optimal solution, which occurs at where? Extreme point. And actually we have seen this before, like when we have y, x, and z, and we had like a line like this, and another line like that, and then the convex set was this here. So this is non-empty and bounded, and now this theorem says, I have explained this before, the optimal solution will happen at one of these extreme points. Good? Okay. Now, let's go to part 2. If S is non-empty but non-bounded, so when S is not bounded, then we might or might not have an optimal solution. But once we have an optimal solution under that case, then that optimal solution again occurs at extreme point. Okay? Like, let me make a graph for a non-bounded convex set. We might have the first half space to be this side, and the second half space to be this side. And then S will be the intersection, and so S will be the intersection, which means this here and this here, and it stays continuous forever. So the system with such a visible set of solution, sorry, the set of visible solution here, the convex set, is unbounded. Okay, now the system, if it has a solution under such a case, then it will be at an extreme point, and in here this is the only extreme point. Okay, so let me make it more general. Let me play with it more. I want to add one more line. Maybe we have another line going like that, and then this is the closed half space. Now we go back, our set will be the intersection. Here we go, this point, and then this point, and again we have unbounded convex set of visible solution. And now the theorem here says if this has an optimal solution, then it will occur at the extreme points. It does not say that the system must have an optimal solution at extreme point. No, extreme point may exist but still the system does not have optimal solutions at them. Okay, but if the system would have such an optimal solution, it must be at one of them. Okay, now number 3. If an optimal solution to a problem does not exist, then either leash y, because S is either empty or unbounded. So the only case where solutions do not exist, that's because there is no visible solution at all, S is empty, or there are many infinite solutions, the convex set of solutions, but it is unbounded. Okay, so if no optimal solution exists, we are not saying that if the set S is unbounded, then there is no optimal solution. No, we are not saying that. In part 3 here it says if an optimal solution does not exist, that's because S is empty or unbounded. Okay. Okay, good. Any questions so far? Okay, good. Let's go to examples. Consider the linear programming problem. This is the very first problem we have seen in the book, which is about the lumber mill producing the finished grade boards and the construction boards, right? X was for the finished grade board, Y was for the number of construction boards. Okay, so we have the linear programming problem. This is the objective function we want to maximize under these two constraints, and we can graph these constraints and take the set of solutions, the convex set, and then easily we will find that it has 4 extreme points. We can do it by hand. Now they are here. Now what we do, we plug in them into the objective function, and then we get that this, and this, and apparently the maximum happen at this point. So the solution says make 3/2 finished grade boards and make 5/2 construction grade boards, and this is the explanation. Okay, this is what I'm saying. So we will say 1.5, which means the units where the board used to be measured with 1,000 feet. So 1.5 means 1,000.5 board feet of finished grade, and 5/2, which means 5/2 times 1,000, 2,500 feet of construction grade, and the maximum profit will be $430 per day. Good. Now, so the idea, go to the extreme points. First, find the extreme points. Okay? Go to the constraints. Draw lines for each constraint. Take the intersection. You get the convex set of visible solution. Get out the corners, the extreme points. Substitute each one of them in the objective function. Then you get the maximum. Then you are done. Easy, huh? But this is not the way to do it in general problems with multi-dimension in dimension 4 or 5 or even 3 is not easy to graph. So we need to learn an algebraic method, a technical method, to find the maximum or minimum of objective function without keeping graphing. And we will do that once we reach the section called simplex method. Okay. Let's keep going. Consider the linear programming problem. Maximize this subject to this constraint. But when you draw the lines and take this greater than or equal, less than or equal, so you will find the half spaces are disjoint, and then S, we talked about in the theorem, is empty. Then we conclude there is no solutions or optimal solutions. No optimal solutions. Okay, so S is empty. Okay, one more example here. Consider the linear programming problem. Maximize this under these constraints. Now, if we draw this as we learned and take the intersection with this and that, Then this is our convex set of visible solutions. Now we have here corner, extreme point, extreme point, extreme point. Each one of them substitute in the objective function, and then we get the maximum happening at 2 points. That's fine. We might have more than one optimal solution. We can take this or that. We can choose. Okay? Now, what does it say here? It says these 2 points, what about them? They are optimal solutions. Okay. The line segment joining these points is xy. Okay, we use this and we use that, and we got this. Okay, just some algebra, some more. Fine. For any point in the line segment we have, okay. Okay. It means it's not only 2 optimal solutions, but there are infinitely many optimal solutions. You see here, the optimal solutions are this one we found here from the table, and this one. Now the objective function has taken a value of 12. Now we are showing here that any point on the line joining these 2 points is also an optimal solution. How we do that? Okay, so any point is here. Assume x is on the line segment joining these 2 points, which means it is lambda times the first one, 1 minus lambda times the other one, and then any point will take that form. So any point here will take that form, and this will be the coordinates. So any point on the green segment, line segment, has the coordinates to be 3 plus 3 lambda, 2 minus 2 lambda, where lambda can be any number between 0 and 1. Okay, so take such any point and plug them here. This is for x, so this is for x, this is for y, and plug them here. This is for x again, and this is for y, and do computations. What you get? You get 12. So the objective function will have the same maximum value at any point on the line segment, the green one. So any point on this line segment is an optimal solution. So we have infinitely many optimal solutions. So this example is to show you that infinitely many optimal solutions may exist. Okay? Now how we find optimal solutions? We will take one more section about basic solutions. We will learn some techniques, some theory, and then we take it to the section after to learn the standard form or the basic form or the simplest form of the simplex method that we use to find optimal solutions for linear programming problems. Thank you very much. This is the end of our lecture today. If anyone has a question, please go ahead.